Imagine a world where machines do more than just perform calculations or follow instructions. They adapt, reason, and even learn from experience. Once the stuff of science fiction and ancient myth, this world is now increasingly part of our everyday lives. The pursuit of artificial intelligence, or AI, has been a journey stretching from the earliest imaginings of mechanical beings to the sophisticated systems that shape our world today. Long before the digital computer was invented, humans dreamed of constructing artificial forms of intelligence. Ancient myths tell of mechanical beings crafted by gods or ingenious inventors, such as the automata of ancient Greece or the programmable music automaton described by the Bani Masa brothers during the Islamic Golden Age. These creations, celebrated in legend and experimentation, reflected a deep fascination with mimicking life and intelligence through artifice. Even Aristotle, with his formalization of logic and syllogism, laid crucial philosophical groundwork. His ideas about means, ends analysis would influence how later generations approached problem-solving and reasoning in machines. Over the centuries, these ideas gradually became more tangible. In 1921, Czech playwright Karel Apek introduced the word robot in his play RUR, giving a name to artificial workers that captured imaginations worldwide. However, the true scientific pursuit of artificial intelligence began in earnest only in the 20th century, when advances in mathematics, logic, and engineering converged to make intelligent machines a realistic goal. One of the most significant early contributors to this vision was the British mathematician Alan Turing. In the 1950s, Turing posed a provocative question: can machines think? His famous imitation game, now known as the Turing test, offered a way to evaluate whether a machine could convincingly simulate human conversation. Turing's work did more than propose a test. It introduced the radical idea that machines could one day advance beyond their original programming, adapting and learning as humans do. This concept of machines that could learn, reason, and improve set the stage for the discipline soon to be called artificial intelligence. The field was formally established in the summer of 1956 at the Dartmouth Conference, organized by John McCarthy, Marvin Minsky, Nathaniel Rochester, and Claude Shannon. It was here that John McCarthy coined the term artificial intelligence, describing it as the science and engineering of making intelligent machines. The conference's ambitious goal was to explore how every aspect of learning or intelligence could, in principle, be precisely described and then simulated by a machine. This event marked the beginning of artificial intelligence as a distinct field of study, drawing on insights from computer science, statistics, mathematics, and neuroscience. At its core, artificial intelligence is a branch of computer science devoted to creating systems capable of replicating human intelligence and problem-solving abilities. An AI system is not just a program that follows a static set of rules. It is designed to learn from data, adapt to new information, and make decisions that previously required human intervention. This allows computers to simulate abilities such as learning, reasoning, understanding language, and even perceiving the world through vision or sound. Over the decades, AI has gone through cycles of optimism and challenge. The initial wave of enthusiasm in the 1950s and 60s was followed by periods known as the AI winters, when progress slowed and funding diminished due to the technology's limitations. Yet innovation continued. The development of expert systems in the 1980s, which encoded human expertise into rule-based computer programs, kept the dream alive. These systems could perform complex tasks in fields like medicine and engineering, demonstrating artificial intelligence's potential to augment human knowledge and productivity. A major turning point came with the advent of machine learning, a subfield of artificial intelligence focused on enabling computers to learn from experience rather than relying solely on explicit programming. Early machine learning models often required significant human oversight. The real breakthrough arrived with the development of artificial neural networks, particularly after 2012. Inspired by the structure and function of the human brain, neural networks allowed machines to process vast amounts of data and recognize patterns with remarkable accuracy. This advance paved the way for deep learning, where layered networks, often with millions of connections, could learn to perform tasks ranging from recognizing faces in photographs to translating languages or mastering complex games. Today, artificial intelligence appears in countless forms, many so seamlessly integrated into daily life that we hardly notice them. Virtual assistants respond to our voices, recommendation algorithms suggest movies and products, and autonomous vehicles navigate city streets. Tools like Grammarly use machine learning and natural language processing to help users write more clearly and effectively. These applications show how artificial intelligence has moved from theoretical exploration to practical reality. touching everything from customer service chatbots to autonomous robots in factories. Artificial intelligence can be classified into several broad categories, each reflecting a different stage of its evolution and capability. The most common form encountered today is narrow or weak artificial intelligence. These systems are designed to perform specific tasks, such as recognizing speech, playing chess, or filtering email spam, and do so with impressive efficiency. However, their intelligence is limited to the problems they are designed to solve and cannot generalize beyond their programming. General artificial intelligence, sometimes called strong artificial intelligence, represents the aspiration to build machines that can understand, learn, and apply knowledge across a wide range of tasks, much like a human. The concept of superintelligent artificial intelligence goes even further, envisioning machines that not only match but exceed the intellectual capabilities of humans. Researchers generally agree that while narrow artificial intelligence is widespread, general and superintelligent artificial intelligence remain goals for the future. Within these categories, artificial intelligence systems are also distinguished by their operating principles. Some are reactive machines, responding to specific inputs without memory or the ability to learn from experience. Others possess limited memory, allowing them to use past information to inform current decisions. More advanced theoretical models, such as those with a theory of mind or self-awareness, exist mainly in the realm of speculation and research rather than practical implementation. Central to the operation of artificial intelligence is the concept of algorithms, a term rooted in the work of the Persian mathematician Al-Khwarizmi. Algorithms are sets of rules or instructions that computers follow to solve problems or make decisions. In modern artificial intelligence, these algorithms are often applied to data, enabling machines to learn patterns, detect anomalies, or generate new content in response to prompts such as text, images, or even music, a process known as generative artificial intelligence. The relationship between artificial intelligence and human intelligence remains complex and the subject of ongoing debate. Intelligence itself is a multifaceted concept, involving the acquisition and application of knowledge, reasoning, adaptability, and creativity. While deep learning systems have achieved remarkable success in mimicking certain aspects of human cognition, such as image recognition or language translation, there are still profound differences between artificial and natural intelligence. Artificial intelligence systems excel when there is abundant data and well-defined goals, but they often struggle with ambiguity, context, and the kind of common-sense reasoning that humans perform effortlessly. The influence of artificial intelligence on society is profound and growing. Artificial intelligence is often described as a key driver of the so-called Industrial Revolution 4.0, fundamentally transforming how we work, communicate, and relate to one another. It offers powerful tools to streamline processes, automate repetitive tasks, and unlock new forms of creativity and efficiency. Yet, these benefits are accompanied by challenges, including the cost of implementation, potential job displacement, and ethical concerns about bias, privacy, and the responsible use of intelligent systems. For those new to the field, the language of artificial intelligence can seem daunting. Terms like machine learning, deep learning, neural networks, and natural language processing each represent specialized areas of study and application. Machine learning refers to the process by which computers improve their performance through experience and data. Deep learning is a subset of this, involving multi-layered neural networks capable of modeling complex phenomena. Natural language processing enables machines to understand and generate human language, while robotics and computer vision extend artificial intelligence's reach into the physical world. Despite its remarkable progress, artificial intelligence remains an evolving field driven by both technological breakthroughs and philosophical inquiry. The aspiration to create machines that can truly think, learn, and reason is as old as humanity's earliest myths, yet only now are we beginning to glimpse the possibilities and responsibilities that such technology brings. Artificial intelligence is no longer just a subject of speculation. It is an active force reshaping our world, offering new opportunities and raising important questions about the nature of intelligence, autonomy, and the future of human-machine collaboration. Imagine a complex web of connections, each point in the mesh receiving signals, evaluating them, and passing along new signals to its neighbors. This forms the foundation of artificial neural networks, or ANNs, computing model inspired by the intricate architecture of the human brain. The motivation behind neural networks is to replicate, in a simplified and abstract way, the brain's remarkable ability to process information, recognize patterns, and learn from experience. But instead of neurons and synapses made of living tissue, artificial neural networks are composed of mathematical functions and digital connections, all encoded in the language of computers. At its most basic, a neural network is an interconnected group of nodes, or artificial neurons. Each node is a small but essential processing unit, loosely modeled after its biological counterpart. An artificial neuron receives one or more inputs, each carrying a numerical value. Every input is multiplied by a corresponding weight, a parameter that determines how much influence that input should have. The neuron then sums these weighted inputs and, in many architectures, adds a bias term, giving the model additional flexibility in processing information. The next step is where the magic truly happens. The sum is passed through an activation function, a mathematical operation that determines the neuron's final output. This output can then be sent to neurons in the next layer of the network. Neural networks are organized into layers, each with its own role. The first layer, known as the input layer, receives raw data numbers that might represent anything from the brightness of a pixel in an image to the value of a stock on a particular day. The last layer, called the output layer, produces the network's prediction or classification, such as identifying whether an image contains a cat or a dog. Between these two are hidden layers, so named because their workings are not directly exposed to the outside. It is within these hidden layers that much of the network's power resides. Each hidden layer allows the model to recombine and transform information from the input data, learning more complex patterns as it goes. The presence of one or more hidden layers distinguishes a simple, single-layer network from a multi-layer network, sometimes referred to as a deep network. The journey of data through a neural network is methodical yet dynamic. As input data enters the network, it flows forward from one layer to the next, with each neuron processing its inputs and sending its output onward. In a dense or fully connected layer, the most common type, every neuron in one layer is connected to every neuron in the next, ensuring that each possible relationship between features can be considered. As the data flows, it is repeatedly transformed, recombined, and shaped by the weights, biases, and activation functions of the network. This structure allows neural networks to model intricate, nonlinear relationships in data, relationships that would be difficult, if not impossible, for traditional algorithms to capture. A key part of what makes neural networks so powerful is the activation function. While a neuron's weighted sum of inputs provides a basic computation, it is the activation function that enables the network to tackle complex problems. Activation functions introduce nonlinearity, allowing the network to learn and approximate a wide variety of patterns and relationships, not just the simple, straight-line relationships that linear models can handle. Without activation functions, even a network with many layers would be limited to solving trivial linear problems. Common activation functions include the sigmoid, which squashes values between 0 and 1, the hyperbolic tangent, or tan-h, which scales outputs from -1 to 1, and the rectified linear unit, or ReLU, which outputs 0 for negative inputs and passes positive inputs through unchanged. Each of these functions has unique properties and is suited to different scenarios, but all serve the critical purpose of allowing the network to model nonlinearities in data. It is helpful to think of neural networks as flexible function approximators. They can learn to map input data to outputs in ways that are not explicitly programmed by humans. Instead, the network learns from data, adjusting its internal parameters, its weights and biases during a process known as training. During training, the network is presented with many examples of input-output pairs. It makes predictions, measures how far those predictions are from the correct answers, and then updates its weights and biases to improve future predictions. This iterative process, often guided by a method called backpropagation, allows the network to gradually refine its understanding of the data and become increasingly accurate. The origins of artificial neural networks date back to the mid-20th century, when researchers sought to capture some of the brain's pattern recognition abilities in computer algorithms. The perceptron, introduced by Frank Rosenblatt in 1958, is one of the earliest and simplest models, a single-layer network that can learn to separate data points into two classes. While the perceptron itself is limited to solving only linearly separable problems, it laid the foundation for more complex architectures. Today's neural networks, with their multiple layers and sophisticated learning mechanisms, are direct descendants of these early ideas. Neural networks come in many shapes and sizes, each tailored to different types of data and tasks. At their core, however, all neural networks share the same basic building blocks, nodes, artificial neurons, organized into layers, connected by weights and modulated by activation functions. The architecture can be as simple as a single layer with a handful of neurons, or as complex as a deep network with dozens of layers and millions of parameters, as seen in modern applications. These architectures can be adapted to a range of problems. For example, neural networks are commonly used for regression, where the goal is to predict a continuous value, or for classification, where the network determines which category an input belongs to. The key distinction between single-layer and multi-layer networks lies in their ability to handle complex, nonlinear patterns. Single-layer networks, like the perceptron, are limited to simple problems, while multi-layer networks can capture the rich, intricate relationships present in real-world data. As data passes from the input layer through the hidden layers to the output layer, each neuron in a hidden layer computes a weighted sum of its inputs, adds a bias, and applies an activation function. This process repeats layer after layer, with the network learning to recombine and transform the input data in increasingly sophisticated ways. By stacking layers of these simple processing units, neural networks build up the capacity to recognize complex patterns, such as the subtle differences between handwritten characters or the nuanced tones in a spoken sentence. An essential feature of neural networks is their ability to automatically identify patterns in data, without the need for handcrafted rules or manual feature engineering. This flexibility comes from the network structure. The connections between neurons, the weights and biases, and the choice of activation functions all work together to allow the model to adapt to the data it sees. In effect, the network learns how to process input data to produce the desired output, rather than relying on explicit instructions from a programmer. Neural networks are a key paradigm in machine learning, and their influence stretches across a wide range of applications. They can approximate both real-valued and discrete-valued functions, as well as vector-valued functions, making them versatile tools for tasks as varied as image recognition, language translation, and financial forecasting. The adaptability and power of neural networks stem from their layered structure, their use of activation functions to introduce nonlinearity, and their ability to learn from data through iterative training. As the field has advanced, many types of neural networks have emerged, each with unique features and applications. These include feed-forward networks, where data flows in one direction, convolutional networks, which are particularly effective for processing images, recurrent networks, which handle sequential data, and many others. While the specifics of these architectures differ, the fundamental principles remain the same: networks of interconnected nodes, organized into layers, learning to map inputs to outputs by adjusting internal parameters. In summary, artificial neural networks are inspired by the brain's web of neurons, but they operate in the digital realm using mathematics rather than biology. Their structure, composed of input, hidden, and output layers, enables them to learn from data, discover patterns, and make predictions. The interplay of weights, biases, and activation functions allows these networks to model the complexity of real-world phenomena. Through training, they become adept at tasks ranging from simple regression to intricate pattern recognition, serving as the backbone of many modern artificial intelligence systems. As we continue to explore the frontiers of artificial intelligence, understanding how neural networks function is a crucial step in grasping the remarkable capabilities and the limitations of today's intelligent machines. Training a neural network is much like teaching a student to solve problems they have never encountered before. The process involves exposing the learner to quality examples, correcting mistakes, and gradually improving performance until the student can apply their knowledge to new situations. For neural networks, this journey begins with data preparation, continues through a series of calculations known as forward and backward propagation, and is shaped by optimization techniques that guide the network toward better answers. Along the way, challenges such as overfitting and underfitting can arise, making careful evaluation and adjustment essential. Everything starts with data. Before a neural network can learn, its data must be carefully prepared. This involves more than simply gathering information. It is a multi-step process that includes cleaning the data to remove errors, normalizing or scaling values so that different features are comparable, and splitting the dataset into distinct parts for training, validation, and testing. If data preparation is neglected, the network might latch onto irrelevant patterns or fail to learn anything meaningful. Feature engineering, selecting or transforming input variables to better represent underlying patterns, and data augmentation, creating new training examples by modifying existing ones, are often used to enhance learning quality. In real-world scenarios, these steps become even more critical. Datasets from various sources can contain inconsistencies, outliers, or missing values, and ensuring consistent pre-processing at every stage prevents the network from gaining an unfair advantage or suffering from data leakage. Best practices call for standardized features, consistent pre-processing between training and testing data, and careful handling of data splits. Only with rigorous preparation can the subsequent steps of learning yield reliable results. Once the data is ready, the neural network's training truly begins. The first stage is forward propagation. Here, input data is fed through the network, layer by layer, with each neuron performing its calculation and passing the result forward. As the data moves from the input layer through hidden layers to the output, the network generates a prediction. At each stage, the network calculates and stores intermediate variables, which will be essential for the next steps. This process is similar to a student making an initial guess on a test based on their current knowledge. After this initial guess, the network needs to assess its performance. This is done by comparing its prediction to the actual answer, using a loss function to measure the error. The goal of training is to minimize this loss, and to do so, the network must learn how to adjust its internal parameters, its weights and biases, so future predictions become more accurate. This is where backward propagation, or backpropagation, takes center stage. Backpropagation is the primary algorithm for training neural networks, especially those with multiple layers. It works by applying the mathematical chain rule, tracing the error backward through the network, and calculating how each weight and bias contributed to the final loss. In essence, it tells the network how a small change in any parameter would have affected the outcome. This information is distilled into gradients quantities that indicate the direction and magnitude by which each parameter should be adjusted to reduce the loss. However, this process is not without challenges. In deep networks where many layers are stacked together, gradients can become extremely small, a problem known as vanishing gradients or excessively large exploding gradients. Both situations hinder learning. Vanishing gradients prevent the network from updating its weights effectively, while exploding gradients can cause unstable updates and erratic behavior. To address these issues, researchers use techniques such as rectified linear unit activation functions, which help maintain stronger gradients, batch normalization to stabilize the distribution of activations, and dropout regularization to prevent over-reliance on particular neurons. With gradients in hand, the network is ready for optimization. The most widely used approach is gradient descent, an iterative algorithm that seeks to minimize the loss function by updating the network's weights and biases in the direction that most reduces error. Think of gradient descent as walking downhill in a foggy landscape, always taking a step in the direction that seems steepest, hoping to find the lowest point, the best set of parameters. At each iteration, the loss is calculated, the gradients are determined, and the parameters are nudged accordingly. This process continues until the changes become negligibly small or a stopping criterion is met. But gradient descent is actually a family of techniques rather than a single method. There are many ways to refine and accelerate the process. Adjusting the learning rate, the size of each step in parameter space is crucial. If the steps are too large, the network may overshoot the minimum. If too small, progress can become painfully slow. Dynamically adjusting the learning rate during training can help the network converge more efficiently. Momentum-based updates give the optimization process a kind of memory, smoothing the path toward the minimum by considering previous gradients. Batch normalization can further accelerate learning and improve stability by normalizing the inputs to each layer. Weight decay discourages weights from growing too large, acting as a form of regularization. Adaptive learning rate methods, such as adaptive moment estimation and root mean square propagation, adjust the learning rate for each parameter based on the history of gradients, allowing the network to focus its efforts where they are needed most. There are even second-order methods that consider how the loss function curves, though these are more computationally demanding. Despite all these tools, training neural networks remains a balancing act. One of the most persistent challenges is finding the sweet spot between underfitting and overfitting. Underfitting occurs when the network is too simple or inadequately trained to capture the patterns in the data. It fails to learn the underlying relationships, leading to high errors on both the training and test sets. Overfitting, on the other hand, arises when the network becomes too complex, memorizing not just the genuine patterns but also the noise and peculiarities of the training data. Such a network may perform brilliantly on examples it has seen before, but falter when faced with new data, a case of low training error but high test error. This struggle is often described as the bias-variance trade-off. A model with high bias is too rigid, missing subtle cues in the data and underfitting. A model with high variance is too flexible, overinterpreting every fluctuation and overfitting. Addressing these issues may involve adjusting the complexity of the network, refining the features provided to the model, increasing the amount of training data, or applying regularization techniques that constrain the learning process. Evaluating how well a neural network has learned is a science in itself. This typically involves splitting the data into separate training, validation, and test sets, and using a variety of metrics suited to the task at hand. For classification, accuracy, precision, recall, and the F1 score are common measures. For regression tasks, mean squared error or mean absolute error may be more appropriate. Cross-validation, where the model is trained and tested on different subsets of the data, helps ensure that performance measures are robust and not the result of a lucky split. Monitoring validation loss, employing early stopping to halt training before overfitting sets in, and watching for signs of data drift all contribute to maintaining a model that generalizes well. Network architecture and connectivity, how layers are arranged and how neurons are linked, also play a significant role in performance. While systematic methods for optimizing these properties are still evolving, it is clear that the structure of a neural network deeply influences its ability to learn and generalize. Even so-called untrainable neural networks can sometimes learn effectively when guided by another network's built-in biases. This approach, where one network provides guidance to another, can help align their internal representations and improve both performance and stability during training. Throughout this complex process, each element from data preparation to gradient calculation, from optimization tweaks to careful evaluation, contributes to the remarkable ability of neural networks to learn from experience. The journey is filled with challenges, but it is precisely these complexities that make training neural networks a fascinating and continually evolving field within artificial intelligence. Artificial intelligence and neural networks are no longer confined to research laboratories or the pages of science fiction. Their influence now touches nearly every aspect of contemporary life, often in subtle yet profoundly transformative ways. Each time someone interacts with a voice assistant, receives a personalized recommendation online, or benefits from a more accurate medical diagnosis, they are experiencing the tangible impact of these technologies. Across industries such as healthcare, finance, retail, and manufacturing, artificial intelligence and neural networks have become essential tools for solving real-world problems, optimizing workflows, and expanding the boundaries of what is possible. In healthcare, the integration of artificial intelligence has brought significant changes to how diseases are understood and treated. Artificial intelligence systems assist clinicians with tasks ranging from analyzing complex medical images to predicting patient risks and suggesting tailored treatment plans. Neural networks, in particular, excel at recognizing subtle patterns in data that might escape even the most experienced human eyes. For example, when evaluating radiological scans or genomic data, these systems can highlight potential areas of concern, flagging them for further investigation by medical professionals. This ability to sift through vast data sets with speed and precision has not only improved diagnostic accuracy, but also opened new avenues for personalized medicine, where treatments are increasingly adapted to the unique characteristics of each patient. Beyond the clinic, artificial intelligence supports organizational decision-making by aiding in resource allocation, staffing, and streamlining healthcare delivery, leading to more efficient and effective care. The journey from laboratory prototype to bedside tool, however, is neither simple nor straightforward. Deploying artificial intelligence in healthcare settings requires rigorous evaluation, robust governance, and careful integration with existing clinical workflows. Ensuring these systems are safe and trustworthy is paramount, as errors or biases can have direct consequences for patient well-being. Researchers and practitioners stress the importance of not only technical performance, but also the transparency and reliability of artificial intelligence systems. This process involves continuous monitoring, validation against real-world outcomes, and a readiness to adjust or withdraw models that do not meet stringent standards. Only through such diligence can the promise of artificial intelligence in healthcare be fully realized, balancing innovation with the imperative to do no harm. Finance is another sector where artificial intelligence and neural networks have made significant inroads. Here, the stakes are high, and the potential for both risk and reward is immense. Artificial intelligence-driven systems are now essential for managing everything from credit scoring and fraud detection to algorithmic trading and risk assessment. By analyzing patterns in transaction data, neural networks can spot anomalies that may indicate fraudulent activity, helping institutions respond swiftly to threats. At the same time, these models are crucial for decision-making under uncertainty, allowing financial organizations to evaluate risks, optimize investment strategies, and comply with regulatory requirements. The ability to process and interpret massive volumes of financial data in real time gives organizations an edge in an environment where information is both abundant and fleeting. The transportation industry has also felt the transformative touch of artificial intelligence. The development of self-driving vehicles, for instance, relies heavily on advanced neural network architectures capable of interpreting sensor data, recognizing objects, and making split-second decisions. These systems synthesize inputs from cameras, LiDAR, radar, and other sources, enabling autonomous vehicles to navigate complex roadways and adapt to changing conditions. In addition to enabling autonomous travel, artificial intelligence is used behind the scenes to optimize logistics and supply chains, ensuring that goods move efficiently from producer to consumer. The result is an interconnected web of smart systems that reduce costs, improve safety, and enhance the overall reliability of modern transportation networks. Beyond these headline applications, artificial intelligence and neural networks play a pivotal role in industries like manufacturing, where they drive innovation and digital transformation. In advanced manufacturing environments, artificial intelligence is used to optimize workflows, predict equipment failures, and automate aspects of the design process. The ability to anticipate and prevent problems before they occur leads to improved productivity and minimizes costly downtime. Similarly, in networking and infrastructure management, artificial intelligence algorithms help predict failures, optimize performance, and ensure the seamless functioning of complex systems that underpin daily life. The arts, sciences, education, and public safety have all experienced breakthroughs made possible by artificial intelligence. In scientific research, these technologies accelerate the discovery of new materials, simulate complex biological processes, and facilitate the development of novel therapeutics. Education benefits from personalized learning platforms that adapt to the needs and progress of individual students, helping to close gaps and foster mastery. In public safety, artificial intelligence systems can analyze data from multiple sources to identify trends, allocate resources, and respond to emergencies more effectively. The creation of generative adversarial networks, or GANs, in 2014 marked a fundamental advance in generative artificial intelligence, enabling machines to produce realistic synthetic data for simulation, training, or creative expression. Business applications are equally widespread and varied. Customer service chatbots, automated personalization engines, and intelligent automation systems have become fixtures in companies ranging from global retailers to fast food giants and streaming platforms. By leveraging natural language processing and machine learning, these systems understand customer needs, offer tailored recommendations, and streamline operations. The result is not only improved efficiency, but also a shift in how companies interact with their customers and manage their internal processes. Despite these successes, the rapid progress of artificial intelligence raises a host of ethical and societal questions that demand careful consideration. Concerns about bias and discrimination are particularly acute, as artificial intelligence systems often reflect the data on which they are trained. If historical data contains patterns of inequality or prejudice, there is a real risk that these will be perpetuated or even amplified in automated decision-making. Issues of ownership and accountability also come to the fore. When an artificial intelligence system makes a mistake or causes harm, determining who is responsible is not always straightforward. The call for transparency, making it clear when content is generated by artificial intelligence and how decisions are reached, has become especially urgent, as highlighted by public opinion surveys showing a strong desire for openness and clarity. Privacy is another flashpoint, with the use of artificial intelligence in sensitive domains raising concerns about the collection, storage, and use of personal data. The deployment of artificial intelligence systems must be guided by principles that respect individual rights and ensure that data is handled securely and ethically. Environmental impact, too, is part of the broader conversation, as the computational demands of training large neural networks can be significant. International organizations and policymakers are responding to these challenges by advocating for frameworks that emphasize transparency, fairness, and human oversight. UNESCO, for example, has issued recommendations aimed at mitigating risks such as bias, climate impact, and threats to human rights. The goal is to ensure that artificial intelligence is developed and deployed in ways that align with societal values and promote responsible innovation. Achieving this requires robust regulations, interdisciplinary collaboration, and ongoing dialogue among technologists, policymakers, and the public. Looking ahead, the future of artificial intelligence and neural networks is shaped by trends that seek to balance efficiency, capability, and ethical stewardship. Researchers are investing in new architectures that reduce computational costs and reliance on labeled data, focusing on multimodal and self-supervised learning. Advances in biologically inspired models hold promise for deepening our understanding of both machine and human intelligence. Open-source models and transparent practices are gaining traction, supported by investments in policy and regulation aimed at harnessing the benefits of artificial intelligence while minimizing its risks. The societal conversation around artificial intelligence is dynamic and, at times, ambivalent. Surveys suggest that while many are concerned about artificial intelligence's impact on creativity, relationships, and employment, there is also recognition of its value in fields such as medicine and data analysis. The challenge for the coming years will be to foster a climate of trust and responsibility, ensuring that the deployment of artificial intelligence and neural networks serves the common good. As these technologies continue to evolve, their applications will only grow more diverse and deeply woven into the fabric of everyday life. The task for innovators, regulators, and society at large is to chart a course that leverages artificial intelligence's transformative potential while remaining vigilant to its limitations and mindful of its broader implications. The promise of artificial intelligence and neural networks is immense, but their true impact will depend as much on how they are guided and governed as on the ingenuity of their design.